All right, so let's get this done with so you guys can start your spring break. Well, maybe you got another class. You guys have other classes? No, just this. That's what I thought. All right, so remember, okay, let's quiet down, everybody. Let's remember that our assignments for this week are due the Monday after spring break, right? So you have extra time. I know you might not want to work on them over spring break, but then you could do them now, right? Or right after class if you want. There is a UTF today. Okay, let's quiet down. Oh, that's not the right time, though. So yeah, you might have to check on the website. I don't have that. That's for yesterday's time. I just changed the Friday, I guess. Remember that those UTF, I put those office hours there every time on the upcoming office hours. And those UTFs are there to help you. And they're getting paid for it. And usually they sit there all by themselves and nobody comes to ask any questions. So you guys should really, utilize them. All right? Even if you want to work on your homework, you could go and bring your computer and just work on your assignments in the room there, and then if you have a question, you could ask them. They'd be right there. Right? So, use all of the resources that we have available. Okay, so yesterday we started into chapter 21 on aldehydes and ketones. We talked about some naming. We talked about the physical properties a little bit of aldehydes and ketones, and we looked at a spectroscopy example, and we reviewed all of the ways that we've learned up to now to synthesize aldehydes and ketones. Okay? Okay, let's quiet down, please. Too much talking. It's rude to everyone else in the room. So today what we're going to do is we are going to first just review quickly from last chapter what happens when we treat aldehydes and ketones with, I guess my slide, I added an extra slide because I forgot to do this one. Carbonyls react with strong nucleophiles. And then we are going to look at two different types of nucleophiles today. One is another carbonucleophile, but it's a much weaker nucleophile, cyanide. And then we're going to look at amines as nitrogen-based nucleophiles. Okay, so that's where we're going. After that, we'll look at oxygen nucleophiles, but that'll be next after break. All right, so let's do a clicker. All right, so here's what we've done so far. I already kind of highlighted this. The next we're going to go into all these different nucleophiles. Let's first carry on. We were kind of reviewing on the clicker how these groups react with strong nucleophiles. What do we get? So if we start with a ketone, or this could be a ketone or an aldehyde, let's just put an R group here, and let's say that R can equal H or alkyl. All right, so if it's an H, it's an aldehyde. If it's an R, it's a ketone. All right, so let's think about the different reactions we could do. Right, we could react this with hydride. Right, let's just use sodium borohydride. And this is usually done in an alcohol like methanol. All right, so what do we get when we react an aldehyde or ketone with hydride?
The alcohol, but it depends on the substitution.
Right, so we get an alcohol. It depends on whether this R group is H or alkyl, whether it's going to be primary or secondary. Right? So we're going to end up with an alcohol. So this is a reduction reaction. Okay, what if we react this with, let's say, methyl lithium. 1 followed by water. Then what do we get? Right, we get an alcohol, right? It's either going to be secondary or tertiary, depending on whether we're starting with an aldehyde or a ketone. Right, so we again get an alcohol, but we've added another alkyl group. Would we get anything different if we used methyl magnesium bromide rather than methyl lithium? So methyl magnesium bromide, this is just like this. No, we'd get exactly the same thing. So we could use either of those to do the same thing. Okay, what if we used this? Minus, so an acetylide anion followed by water. Huh? Nope, not a carboxylic acid. We can get carboxylic acids from alkynes if we do that oxidative cleavage. But in this case, the alkyne, it's an acetylide anion, is just acting as another carbon nucleophile. So it's just going to get an alcohol, right? But that alcohol is going to have an alkyne attached to it. And so we have this R group. So we get this, right? It's just a nucleophile. It's doing the same type of addition reaction as the Grignard does, or as the organolithium. Yeah?
Is acetylide strong enough to debrominate water?
Yes, absolutely. So the pKa of water is 15.7. Acetylide is 25.
So what do you run this reaction?
So most of these types of reactions, other than the sodium borohydride, have to be run in something like THF or mixture of THF and hexane or something like that. So they have to be run in an aprotic solvent. And that's why we always have these two steps, except for the sodium borohydride, that's much weaker, but all these other ones, we always have two steps, 1 and then 2. Because remember, those have to be sequential. Because if we add water in together with the acetylide, it'll just protonate the acetylide. Or water in with the methyl lithium, it'll just protonate the methyl lithium and we won't get a reaction. Okay? All right, so what if we go down to the ester? Okay, what if we just follow some of the same things here? What if we use sodium borohydride in methanol? Primary alcohol? Oh, we get no reaction. All right. Sodium borohydride is not a strong enough hydride reducing agent to react with an ester. Okay, so what do we have to use instead? Lithium aluminum hydride. Okay, and in that case, we get an alcohol from this side, and then usually we don't really care about this other one, but we do get the other alcohol as well. Yeah?
We'll also be able to do the same thing with like a Grignard reagent.
So, well, yes, we'll do that. We can do that next. We can still add a Grignard reagent to an ester, but it won't give this. Okay. Right? Let's do one more reduction though. What if we do, I'm going to link it all the way over here. What if we do this reduction with dibal followed by water? It stops at the aldehyde. So it stops after a single reduction instead of two reductions. Oops, that's not the right. I was doing the one from above. So we get the aldehyde, plus we'd also get the methanol from the other side of that. Okay, but it just stops after one reduction. With lithium aluminum hydride, it gives this aldehyde as well, but it immediately reduces to the primary alcohol. All right, so what if we add, let's use, oops, that's a 3H2 ethyl magnesium chloride followed by water. And let's just say we're going to use an excess amount of this, at least as much as it needs to react as many times as it can. All right, then what do we get? Tertiary alcohol. Right, because it adds once, eliminates methoxide to give a ketone, and then the ketone reacts again. Okay, so this gives a tertiary alcohol. Yeah, question?
On an exam, if it doesn't say excess, do we just assume that it only runs the first reaction?
Yeah. Well, I think, okay, that's a good question. So the question was, if it doesn't say excess, or doesn't say 2 times, or something that's indicating more than 1, should you just assume that it will add only 1? Yeah, that's tricky, because what if I want that? Since we ask you whether you know whether it'll add 2 times or not without saying it'll add 2 times, you know, I think in all of these cases, you know, it's reacting as far as it will with the reagents that are given. Okay? But usually I'll say 2 times or excess or something like that. Yeah, question?
Would this reaction also produce methanol or no?
Yes, it would. Because that first step, right, it goes to the tetrahedral intermediate, the electrons come down, it kicks out methoxide, which then gets protonated in the last step. So yeah, we can write that in if we want. Sometimes we just kind of neglect that because we're paying attention to the main organic piece that we're trying to make. Yeah?
Why would that produce the alcohol as opposed to the ether? Oh, just kidding. I read it backwards.
Okay, all right. Ha. Good joke, yeah. All right, so what else can we add to this ester? Well, that's most of the stuff we know so far, right? We're going to learn some more, but not today. We're going to have to wait till after spring break to learn any more ester reactions. Oops, I didn't want to do that. Okay, so here's the types of nucleophiles we're gonna look at now. Okay, all of these are weaker nucleophiles than what we've seen so far. Grignards, organolithiums, acetylides, hydride. All of these are weaker than that. Okay, and so like we said last time, in many of these cases, because the nucleophile is really not strong enough to react directly with the carbonyl, we have to use a catalyst, usually acid, to make that carbonyl more reactive. Okay, so let's look first at the addition of cyanide. Okay, so this is the structure of cyanide. Okay, if once we've added it into a molecule, do you know what it's called then?
An
Not an azide. An azide has 2 nitrogens. A nitrile. Okay, so cyanide is the anion. A nitrile is the part that's attached, once it's attached to an organic molecule. Okay, so if we react cyanide with a ketone or an aldehyde, let's just draw it like this again, and we'll say this is R prime, and let's say that R prime can equal either H or alkyl, so we'll just add together our aldehydes and ketones here. When we do this reaction, the cyanide is going to mostly come from sodium cyanide, right, which is just an ionic compound, right? So sodium plus, cyanide minus. But that doesn't do it all. We have to add a little bit of acid to this. Okay, and so this is really just a small amount. Okay, and when we do that, the type of compound that we get is just an addition reaction. We add the cyanide to the carbonyl carbon. We end up adding a proton onto the oxygen. Okay, same kind of reaction we've seen. It's just an acyl addition reaction. This type of product is called a cyanohydrin. The cyanide and the hydrin is for the OH. All right, it's kind of interesting that this type of product, well, if we treat this type of product with hydroxide or a strong base, it'll just go backwards. Okay, it'll go back to the carbonyl and kick out cyanide. Right? And in fact, if you've ever heard that certain like almond pits or peach pits, or if you break it open, that little seed inside, that those smell like cyanide or something. Has anybody ever heard of that? And in fact, those plants produce, it's usually something more complicated than this. It's got like some sugars and stuff, and there's some pictures in the book. I didn't redraw them out here, but they have this cyanohydrin. And so they don't really hold cyanide themselves, but they can kick out cyanide. And so that's why they say you're never supposed to eat those things too. So don't go out and try it now. Okay, so the way that this works follows kind of our normal pathway. This cyanide has a pair of electrons. It's going to attack the carbonyl carbon. We're going to go to a tetrahedral intermediate. O minus. We have our cyanide. And then what happens is this mixture of cyanide and a little bit of HCl generates some hydrocyanic acid. And so that's what they show, at least in the book, as being the proton source here. So it goes like this, forms some cyanide again that can go and react further. All right, so if you just have HCN, the reaction doesn't really take place. Okay, because it's not, HCN I think has a pK of about 9 or something like that. It's not acidic enough to have an appreciable concentration of cyanide anion in solution. All right, so we mostly use sodium cyanide. We add a small amount of acid, so that helps protonate. Okay? All right, so cyanohydrins, there is a reaction they show in the book. I think we'll bring that up later because it's a reaction of the actual nitrile, and we haven't learned any of those things yet. Okay. To amines, so nitrogen nucleophiles. All right, and so in these cases, we're going to react an aldehyde or a ketone, and we're going to first look at what happens when we add a primary amine. So have you learned primary, secondary, or tertiary amines before? Well, they're not exactly. So a primary alcohol, how do we classify a primary alcohol?
It's characterized by the carbons.
Yeah, the number of carbons that are attached to the carbon bearing the alcohol, right? So primary alcohol just has a OH and then it has a CH2 and then one carbon attached to that. Secondary is the OH attached to a CH that has two carbons attached. Okay, amines and amides, we'll talk about later, are a little bit different. Okay? And these are categorized by the number of alkyl groups that are directly attached to the nitrogen. Okay, so this is a primary alcohol right here. This is a primary alcohol down here because the nitrogen in both cases have a single carbon attached. All right, so if we had something like this, diethylamine, this nitrogen has two carbons attached. This is a secondary amine. If we have three groups, triethylamine, like this would be a tertiary amine. And then if we have four groups, right, has to have a plus then. This is called a quaternary ammonium ion. Okay, so this is quaternary ammonium. Right, remember ammonium itself is NH4 plus, the ammonium ion. Okay, so first we're going to look at the reaction of primary amines. And then work with aldehydes and ketones. Then we're going to look at secondary amines. Most of it's the same, but there's one small difference at the end. Okay? So the way that we can do this is what we essentially do. Here, let me just, I don't know if I have enough room here. I'm going to redraw that amine, and I'm going to redraw it right up here. Nitrogen, H. Here's the primary amine. Like this. What we're going to end up doing is forming a water molecule right here, okay? And then the nitrogen is going to replace the oxygen. Okay, so the product we get is going to look like this, with a carbon-nitrogen double bond. And we lose a water molecule. Okay? This type of product is called an imine. And imines are important in biology. For example, you can look in the book, it has this too. So here I could draw this out, I think. Okay, let's see if I can do this. So, 1, 2, 3, 4. 1, 2, 3, 4. So this molecule, oh, I did that wrong. Dang. Thought I had it. Oops. Okay, let me just do a bunch of these. Okay, so then we have to have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. I think it's like this. Okay, this is a double bond, double bond, double bond, double bond. Okay, so this molecule is called retinal. Okay? And where do you think it comes from? It's in your eyes, but where else? What produces it? Right, so this is essentially half. If we took this aldehyde and we drew the whole thing over here, but in reverse order, we took out the two oxygens and we made a double bond between these two pieces. We would have beta-carotene. which is the orange color in carrots. Okay? So beta-carotene essentially gets cut in half to form retinal, and then retinal reacts with, and I'll just draw it like this, with a protein called opsin. Okay? And it forms an imine bond between the protein and the aldehyde of the retinal. Okay, so that forms, I'm just going to do kind of an R for that whole thing. And this is the protein here. Forms an, that's how the retinal gets attached to the protein. Okay? But in the middle of the protein, in fact, the middle, one of these middle double bonds switches to cis. And this is like this visual chromophore. This is what absorbs black and white light in your eyes. And when it absorbs the light, it switches from a cis to trans double bond. And that's the trigger that sends to your nerves. Oh, I thought they were talking to us. They were just going, oh, that class sounds really interesting. We're going to listen in and make some comments. So yeah, this kind of imine is very important in biochemistry. Okay, so let's look at how this gets formed. All right, so we're going to add one more step than they do in the book if I can fit it all into this little space right here. Okay, so the first step, just like we've done in all of our times before, the nitrogen with its non-bonding electrons can attack the carbonyl carbon. Okay, I'm going to go over this way, draw these a little bit small, so hopefully I can fit it all in. Here's our H. Our nitrogen still has both of its H's attached. All right, so what kind of a, well, I'll just do it. So we have a plus on the nitrogen and a minus on the oxygen. Okay? So now what has to happen is, let's think about what has to happen. All right? So if we look at the product up above, what do we need to have happen? Oh, there it is. All right, if we want to get to a carbon-nitrogen double bond, if we look at this molecule here, right, we know that we want to keep the nitrogen to get to the product, right? We want to get rid of the oxygen. So what kind of reaction steps can we do that will keep the nitrogen but will get rid of that oxygen? How do we get rid of that oxygen? Yeah, we want to put some protons on it, exactly right. So if we put one proton on it, we got an OH. Is an OH a good leaving group? No, what can we do to make it into a good leaving group? Right, make it into a water molecule. So we have several just simple acid-base steps that we have to do in order to deprotonate the nitrogen, because right now the nitrogen is the better leaving group because it's protonated. And if the nitrogen is the leaving group, what's going to happen to the structure if it comes off? It'll just go straight back to where we started. Right? So these are all in equilibrium. Okay, so we want to eventually protonate the water twice, and we want to deprotonate the nitrogen. So we have a number of, oops, can't do it just with a lightsaber. We have to do several acid-base steps. Okay, so the first step we're going to do is we're going to protonate the oxygen, okay, because it's quite basic. And we're just going to use this H plus up here. Okay, and so this oxygen is going to get protonated.
That's
Yeah, go ahead.
Is there any reason why the oxygen can't deprotonate the hydrogen on the nitrogen?
Yeah, good question. And in fact, that's how I had kind of drawn it in my initial notes. So the question is why, since they're right next to each other, why can't that, the O minus, here I want to go back to, well, let's use this one. This is the one I always like too as well. I always said, oh, here, that I'm giving you guys a finger, see? Dang, nobody even laughs. So why does the oxygen just not reach over here to get the hydrogen, right? And that could maybe happen, but it's all surrounded by solvent and everything too, so probably the solvent or even the amines that are in here are probably going to be the relays for the protons. And plus, I want to show a different intermediate along the way. Okay, so there's one. So the next process is going to be to deprotonate the amine. And I'm just going to show this as having an amine here. I'm not going to draw the whole thing. It's probably just the amine we're starting with up there is going to be the base in here. So this is going to pull this off. And then through all of these steps, we've kind of finally gotten to essentially what is just a neutral tetrahedral intermediate. Okay? So we've gone through 1, 2, this is our third tetrahedral intermediate. They've all just been acid-base chemistry so far. Okay? So now we want to get rid of the oxygen. Okay? So we have to protonate that one. All right, so I'll just use our H plus here again. So this is what, this is a general thing that we've learned before, right? And, gosh, this is going to be... All right, so then we have our leaving group. Okay?
Just a quick
Yeah.
question.
Mm-hmm.
So we showed the 2 protonation steps. There's another reactor between them. Does it really matter the order here? Can we just have the 2 protonation steps at first?
I think the order does kind of matter. Because it just depends upon which is more acidic or basic. Okay. In the process. So up here, the oxygen that's alkoxide is the most basic, right? And so it's going to react first. So we're kind of going gradually toward this neutral one, and then we're starting to reprotonate. If we started to protonate already over here, then we got 2 pluses almost next to each other. It's going to be less stable as well. Okay. And notice if we were going to go from, so if we're going to go from the neutral one, really there's 2 possibilities as far as protonation goes. We can either protonate on the nitrogen, goes back to here, right? Or we can protonate on the oxygen, and it goes up to here. Okay? Which of those, from what you've learned before, which one do you think is more likely to happen? Which is more basic, an alcohol or an amine? The amine is actually more basic. Okay, so at this point, the equilibrium could lie back towards our reactants. Okay, but we only have to protonate a little bit here to form this to get that water molecule to leave, because that's the best leaving group we could have in this whole thing, too. And we'll talk about later how we can, what things we can do to shift the equilibria in some of these reactions. Okay, so the water molecule's ready to come off. Okay, and the way that cation that's then generated gets stabilized is it can accept the protons from the nitrogen. Okay, it's just a different resonance form, but this is the way we usually draw it. I'm going to see if I can squeeze it back in over here. Okay, and so we've lost water, and now we have the nitrogen. We now do have the carbon-nitrogen double bond, but we have an H on it, and, oops, I wrote this group in the wrong place. That should just be an H there. And here's where I have that alkyl group. So we have a plus on the nitrogen. Okay, so then what do we need to do to go from here, if you can find it, this nitrogen here, to our product up here, other than just rotate around this bond too? Yeah?
Shouldn't the hydrogen be on the nitrogen and not the carbon atom?
Well, I do have a nitrogen on the hydrogen on the nitrogen.
Oh.
So this is the one on the nitrogen that you can decipher that that's a hydrogen. And then there's a hydrogen up there, and that hydrogen up there is the hydrogen that started next to the aldehyde. Okay? I just didn't draw it in every time. There'd be a hydrogen here, there'd be a hydrogen here, right, along the way. Okay, so what do I have to do to get from here, from this species here, to our imine product? I just have to deprotonate it, okay? So, we're just going to, we can go up this way, and that's just going to be a deprotonation. I'm just going to draw this amine again, NH2. I need to put less on the slide here. Comes in here, and that deprotonates that, and we go to our product. So I'll do like I did yesterday. So let's map out. Here we go this way, we go this way, we go this way, we go back this way, and then we go up this way.
Yes.
Within that spaghetti of a mechanism. All right? Does everybody follow that? So mostly what it is we do our nucleophilic attack to form a tetrahedral intermediate. And then from there we do a bunch of acid-base chemistry, ending up at the point where the oxygen is now a water molecule, so we can get rid of it. All right? When we get rid of it to stabilize the cation that would form if I just lost the water molecule, it comes down to form the carbon-nitrogen double bond that we see in the final imine product. Okay? All right, so let's just squeeze in down here this other reaction. Oops, I do that every time. Let's just predict the product. Okay, we'll put it right down in here. Okay, so we have a ketone this time. We're reacting it with this primary amine. So what's the name of that amine? Aniline, right? And what do we get? Okay, so really all we have to do is we're going to take this water molecule off right here, and we're going to connect that nitrogen, this nitrogen directly up to this carbon with a double bond. Right, so you can position, you can just kind of erase those groups. Here, we can do it like that. I'm going to do it like that. Okay, so here's this. Here's our H2N. Here's our amine. Okay, I just drew them next to each other. Now what I'm going to do is I'm just going to erase the oxygen and the hydrogens, and I'm just going to make a really long double bond right here. Okay? But that's as simple as that. We're just taking a water molecule out of the middle there, right? And then it can shrink back down afterwards. All right, so let's stop there. After spring break, we'll see there's a slight difference to get to a neutral species when we're using secondary amine. All right, so have a good break. Come back all pumped up and ready to learn some more.